Here, we basically show the steps to formulate a numerical model, basically. It doesn't have to be for um, petroleum reservoirs, but of course, the focus here is on reservoir simulation. So I will be explaining this within the context of how to come up with a reservoir simulation model. So the way to come up with that model is to start out by visualizing the physical mechanism for the system, all right? And you base that on familiarity with the related problems, either in the field or in other fields. So what is the problem we're talking about here? The physical mechanism is basically fluid flow in porous medium. So flow through a porous medium. What analogy do you think we have to other fields? The easy one is heat conduction, right? If this is a rod and you apply high temperature here, then heat flows, right? Via conduction. If it's a porous medium, you can have heat flowing through advection, and you can also have heat flowing through radiation. So there is heat conduction through rods. And this flow problem is actually very similar to heat conduction problem. And most of the analytical solutions we have for fluid flow in cylindrical systems and all those radial flow solutions, linear flow solutions, flow in fractured reservoirs, many of them actually come from Kaslow and Yiga, which is a book on heat conduction. So we look at the governing equation. Ours is of the same form. The partial differential equations look similar. And we go grab the analytical solutions from those problems and substitute the parameters for temperature with our parameters, which are parameters for pressure and others. Then we recall the physical laws that govern whatever problem we are trying to model. Here is fluid flow, and we think of their mathematical form. So for fluid flow, we have the governing, we start out with the constitutive equation, and we'll talk about that shortly. And part of the flow, the equations that govern 1D flow is Darcy equation. So Darcy's equation is the constitutive equation we actually use, and it's of the form Q equals minus K over mu grad P, right? If you go check out the equation for the constitutive equation for heat conduction, similar thermal for T, it's minus thermal conductivity, all right? So K over mu can be seen like the equivalence of thermal conductivity gradient of temperature, or they're similar. So that's the form of the constitutive equation. Then we identify the significant variables like thermal conductivity for that, for heat flow, in our case, permeability, viscosity. Then sometimes we do dimensional analysis, so we have the equations in a dimensionless form. We can have dimensionless flow rates. Then we choose a differential element of time or space, and this basically means we discretize the system in space. Remember those grid blocks we talked about before, and each grid block has a volume, and we're basically, this is a representative volume element, REV, a representative elementary volume. Very small, that's why we're saying it's a differential element. Small enough to be able to approximate the domain without introducing large truncation errors. And we can do the same thing in time. We discretize time into delta t's and space into delta v's. And then write out the governing equation for how the variables change within that element. And this is precisely how we came up with the constitutive the conservation equation. The equation that governs the conservation of mass is this. So this is your representative element with volume delta V, infinitesimally small element, and we figure out flux in, flux out. And basically we use the law of conservation of mass, that mass out minus mass in, so this minus this equals what is conserved in the element. And when you go through the derivations, you will divide through by delta V, which is delta X, delta Y, delta Z, and eventually you will have the governing equation in terms of these discrete quantities, delta T and delta V. Right, that's the conservation law that governs fluid flow. Then what you do is to take the limits as the delta V, which is delta X times delta V times delta X times delta Y. I mean, delta V is delta X, delta Y, delta Z. As that gets in the limits as it tends to 0, same thing with the limits as delta T tends to, which is time, tends to 0, then we come up with a differential form of the same equation, and that's the one that we use all the time as a conservation law. And del dot rho, that's the velocity, which is Q over mu grad P. Here you have area. If it's Q, you have area. If it's V, you don't have area. Equals 0 if there is no source or sink. And that's the differential form of the governing equation that we'll be solving for single phase flow. That's your conservation law. It describes the conservation of mass as fluid flows through the porous medium. You can't solve this equation by itself. You need boundary conditions. So Dirichlet boundary condition, pressure at a boundary or all of the boundaries can be a fixed value, maybe 7,000 psi or whatever, or you can specify no flow boundary, meaning flow rate at all the boundaries is 0. That's a natural boundary condition. You don't need to do anything. And then you provide initial conditions. Pressure everywhere is a certain value, but you can assume it's also 7,000. And the initial conditions plus boundary conditions together with the differential equation completely defines your problem. Then if needed, you can convert all these variables to the dimensionless form so you can work with, so it has no units basically. And then you can solve this problem analytically, which is what we do in well testing. I will come up with equations for pressure as a function of space and time everywhere in the domain under certain assumptions. And those are the analytical solutions. Analytical solutions typically will be one equation as a function of pressure and different parameters. So you have a mathematical expression to evaluate whatever you're looking for. That's an analytical solution. But for numerical solution, there are several equations for these different grid laws in the domain, and you can't solve it by hand. You need a computer algorithm that solves those systems of equations for all of the grid laws in the domain before you can find the solution to that problem. Good. And I'll defer the conversation on this airplane analogy to the next video.